Laskar, and he's currently a research associate at the Laboratory for Atmosphere and Space Physics at the University of Colorado. He did his bachelor and master's degree in physics from Assam University in India, and then he did his PhD at the Physical Research Laboratory, also in India, in 2014. And after receiving his PhD, he worked in Germany at the Leibniz Institute of Atmospheric Physics in Cologne. He worked there for 4 years, and then following that, he joined LASP in March 2019, working on the NASA Gold mission. And his research interest is mainly on the thermosphere, ionosphere variability due to forcing from above and below. And today he's going to present his research related to data assimilation.
So shall I go ahead?
Go ahead and start sharing your screen.
Yeah, thank you, Nick, for a nice introduction, and thank you all for joining. Let me share my screen. So hope everything looks good. Can you see the screen well?
Yes, it looks fine.
Okay. So yeah, thank you everyone for joining. And today I'm going to talk about improving thermosphere ionosphere in WACMAX by assimilating gold disk temperature. So myself, Fazlul Laskar, and I've been here is a list of partial list of all the people that have been contributed in this work, and like particularly I've been very fortunate to be working with these wonderful people, and particularly Nick Peratila has been very helpful in explaining and answering all the questions about WACMAX and DART, and Michael Kodrescu from NOAA SWIPC. He has a lot of experience with the modeling and data assimilation, and he has also been constantly helping me in this project. And so the Richard Estes, who is from CU LASP again, he's the PI of Gold Mission. He's very supportive and he and all other collaborators, some of them are listed here. They have been very helpful in pointing out a lot of possible issues or possible artifacts in the data that we apply at different points, and in solving those problems and artifacts. So yeah, I didn't list many of the other contributors. So the plan of my today's talk is first I'll give some introduction to the gold mission, and some introduction on temperatures from gold, and then I will go to why we need to assimilate the gold and what are our objectives. And then we talk about the model and the data and the methodology that we are using. And then I will present some results from observing system simulation experiments that using gold data and low atmosphere data. And on the step 5, I will be doing some assimilation of actual gold data and present some results on this. And finally, I'll summarize with some conclusions and future directions. So I believe most of you know what is Gold Mission. It has already completed 3 years of observations, and the gold, as you know, it is in a geostationary orbit at 47.5 degree west longitude and at the equator. And it has two identical imaging spectrographs in the UV region. And from the measurement point of view, so what is shown on the right is this is the SES 14 satellite, and this is the gold instrument. And what we see here are the disk images from this instrument. So from the measurement point of view, we see spectra of emissions. And from these emissions, we derive the level 2 data products. So what I have listed here are mostly the level 2 products. I think you cannot see my cursor, so let's go to the, yeah. So yeah, so these measurements are the level 2 data products that we get from the gold mission. The main products that I'll be using is the T-disk, which is derived from the N2 LBH emissions. And other than that, we have like other level 2 products like O by N2 that I also will be using in this work just for the validation. And in addition to that, we do have like other measurements from LIMP, but I'll not discuss on those here. So here is an example of gold data that we have been talking about, the temperature, disk temperature. So on the left one is the just for a particular half-hour scan of the disk. And this is a bit smoothed version, so you see all the features very well. And on this particular day, there was a minor geomagnetic storm, and we did see like increased temperature in the northern high latitudes. And in the middle, what I'm showing is the random uncertainty associated with every points in the disk. And you can see the uncertainties varies from 20 to 100, about 100, but most of the uncertainties are below 50 Kelvin. And yeah, and also on the right, what I'm showing is the solar zenith angle variations over the disk. So what is the importance of solar zenith angle variation? Um, Solar zenith angle actually varies a lot over the disk, and with the variation of solar zenith angle, the altitude of the peak altitude of the emission layer changes. And this, what I'm showing here is what we call is the contribution function that shows how, with respect to solar zenith angle, how the layer shape and the peak of the layer is changing. And it has a lot of implications in the data assimilation. And so because this data needs to be, the temperature data needs to be distributed among all the spatial levels in the model as per these contribution functions. And this contribution function also varies with emission angle. What this I'm not showing here, but for emission angles below 50 degrees, there are like variation with respect to emission angle is negligible. Okay, so yeah, now we do have a lot of temperature data. So before going into the assimilation, what I wanted to show you here is that do we see any geophysical variations in this temperature data? And for that, I am presenting here some of one of our recent results that published in GRL. And what I'm showing here is like in the y-axis, the sub-satellite local time, and x-axis is days. This covers around 2.5 years of observations from the gold. And these temperatures are being in like 20 degree in latitude and 10 degree in longitude, and that's what is shown here. So in this one, in addition to temperature, what I'm plotted is the AP index, the black one, and the purple one is the F10.7 solar flux. And in this plot, we can see the smooth seasonal variations. And also we see when the F10.7 was higher, there is increase in temperature. But in addition to that, what we see, like whenever there is a peak in the AP index that is shown by the black lines here, you can see the temperature get increased. And And that's what we have observed, like whenever AP is greater than 8 nanotesla, we do have a signature in the temperature. And in general, we see that between 13 and 15 local time, the temperatures are higher. That's what we have observed. Okay, so since we see that there is a correlation between AP index and the temperature, so what I'm showing here is how this correlation varies with um, the activities, different geomagnetic activities. So here two groups are classified. One is having AP between 8 and 14, the blue one, and the other one is AP greater than 14. And we see when the AP is higher, the correlation between the temperature and AP is much higher. And for weaker events, correlation is weaker. And also, we have observed, like once we remove the seasonal variations and then we plot in terms of latitude, after the deviations from the seasonal variation, we can see that for weaker events, like for between 8 and 14, temperature enhancement is smaller. But for stronger events, like whenever AP is greater than equal 14, the temperature enhancement over all the latitude is higher. And so this kind of temperature enhancement over all the latitudes can be explained from the circulation change point of view during the storm time circulation change. And that's what leads to this kind of temperature enhancement over all latitudes. And another great thing about the gold mission is that in addition to wide latitude and longitude, it does provide us a good local time coverage. And this is what we show here is a temperature variations for geomagnetic events having AP greater than 20 nanotesla. And the green one is the quiet time variations. And what we see here is like in x-axis the local time, and we see that overall the strong storm time variations are higher, storm time temperatures are higher. But if we take a difference between them, like the active and the quiet time, we say that we see that morning temperatures are higher compared to the afternoon ones. And this also, there are like a lot of implications from this, like it could arise from the day-night difference between the energy deposition, and also that the nighttime circulation will be stronger because of the uh, less solar influence in the daytime. So this is very interesting, and this has been possible because of the rich coverage of the rich local time coverage of the gold at a particular location. And during this time, we have ruled out that it is not arising because of the F10.7, because they are nearly similar in both the cases in all the. So if in about we have seen like the 20% increase in the morning, like it was like 23 Kelvin high in the morning compared to afternoon. Okay, now that we have seen that the gold provides us a data set that has a lot of geophysical variabilities in them, so it's good to have them, assimilate them, and see if we can improve the thermosphere, ionosphere in the assimilation models or in the whole atmosphere model. And why? So before going to assimilation, why do we need an assimilation? So to better understand thermosphere, ionosphere, what we need is a great set of observations or measurements that is available at every location and time. And we know that kind of measurements are not possible. We have a second option that is like we can have a perfect model that can generate everything, whatever we want. And that kind of perfect model is also not possible. So in the absence of both these extreme scenario, a realistic solution would be like combine the experimental data available in a with a model in a data assimilation framework. And those data assimilated observations will give us more near realistic parameters of the whole thermosphere. And we are pretty much familiar with some of the famous examples of lower atmospheric data assimilations, like the ERA 5 and MERA 2. And so the aim of the present investigation is to assimilate gold disk temperature and see how we improve the thermosphere, ionosphere. And so for this simulation, I'm using a forecast model. So for the forecasting of the observation, I'm using whole atmosphere community climate model, WACA-MAX, the version 2.1. And I believe most of you are familiar with it. It has a like 2 by around about 2 by 2 latitude longitude resolution, and it extends from surface to about like 500 kilometer for the low solar activities. And so the gravity waves in them are parameterized, and it does have a self-consistent atmosphere, and also it can be forced by the lower atmosphere and solar and geomagnetic forcings. And so for the data assimilation, I'm using WACA-MAX as the focus model, and for the filtering purpose, I'm using the assimilation purpose using data assimilation research dashboard, what we call DART. And for the current assimilation, we are using ensemble adjustment Kalman filter with 40 members uh, and with 1 hour assimilation step. And what does a simulation do is actually, so we do have, like, imagine we have a initial condition from a previous run of the model, and then we have, for a particular time step, we have observations from all these gold and lower atmosphere things. And once we put these observations in the data assimilation system, it generates the analysis by updating this initial state. And so once we have an analysis, then we run the forecast model and we get the next step, initial states. And again, we do use the same initial step, then I do the assimilation, get the next analysis state. So that's how it repeats and gives us the uh, assimilation at every assimilated state at every time step. And more details about DERT and ensemble adjustment Kalman filter can be found in these two links, and in this link and this paper. So the quality of a assimilation or a forecast depends on how exactly we know the present condition. And here I'm quoting a paper from Lawrence 1963, and the paper showed that unless we know the present condition exactly, we will not be able to forecast the future uh, in better. But in the absence of, like, if we don't have, to have a better estimate of the present, we need a lot of good observations. And so we are fortunate to have, like, currently we do have a lot of observations from the um, different lower atmospheric and thermospheric missions. So in this plot, what I'm showing on the top is geolocations of the observations for a particular 1 hour period, like 15 UT. So it's plus minus 30, around 15 UT. And this is for a particular day. So in this 1 hour observation, the red one is showing the gold uh, geolocations, and the other observations are the, these ones are listed below. So the bottom plot showing the number of observations with respect to pressure, and we see like about 1.5 million observations per day are roughly assimilated. And gold is, like, it's adding up thermospheric observations in this assimilation, and gold data is available from 6 to 23 UT. with varying disk coverage at different times. So for the assimilation, what I'm using is two different kind of assimilation. The first one is observing system simulation experiment. In this one, what we do is we generate synthetic observation based on the error properties of the actual observations. And we use that synthetic observation to assess the performance of the assimilation. And on the second one, what I will show in the show later some results from it, is we do actual assimilation of the gold temperatures. So this is for some of the experiments that I listed here for the observing system simulation experiments. So what we are doing is, like, for the experiment one, we call it true state, which as a solar flux is about 76 SFU. And for the assimilation run, this one is assimilating only lower atmospheric synthetic observations. So these are the observations on the right is shown. And these are some of the solar flux conditions and the geomagnetic conditions that we use with some spread in the over the ensemble. So the second one is only for the lower atmosphere, and the third one is lower atmosphere plus gold, where we are adding the gold temperatures. So idea is to test, like, in this assimilation run, we are using 100 solar flux unit, but the data that has been used corresponds to 76 solar flux unit. So we want to see, like, how the thermospheric conditions goes near to the 76 solar flux kind of things. So um, this is an example of a particular our true state that we derive from the Wacom-X. And from this true state, we derive the synthetic observations based on the error properties of the gold. And once we assimilate these synthetic observations, on the right is shown the analysis state, and on the top right is the forecast state. Remember, this left side, we have a condition, solar flux condition of 76, and on the right side, we have like 100 SFU. And we expect to have higher temperatures on the right, but because of the assimilation, we do see that there are a lot of similarities between the uh, analysis and the true state. And so this is another example of the temperature profiles from all the three experiments. So this blue one is the lower atmosphere, green one is the true state, and the red is the lower atmosphere plus cold. And we do see, like this green one was for 76 SFU, but the blue one is for 100 SFU. And the red is also 100, but because of the assimilation, we see that it is getting closer to the uh, true state. And that shows that our assimilation is working and is driving the model in the right direction. And these are some other, like, diagnostics of the assimilation. So what is shown here is 5 days of data. And these points are where there are gold observations available. And so the top one is the RMS error, and the bottom one is the bias. And you can see, like, compared to blue one, which is lower atmosphere only assimilation, the lower atmosphere plus gold, which I'm showing, is the red one, the LG. That one has much better RMS error. And the green one is actually the forecast. So with respect to forecast, the analysis is doing better. And with respect to low atmosphere only assimilation, it's doing much, much better. So similar is the case for the bias. And we see that the bias is improved much when we assimilate the gold temperature. And so these are some of the numbers, like we do 5% improvement in RMSE compared to forecast, and we do 20% reduction in RMS error compared to, like, the lower atmosphere only assimilation. And similar is the case for the bias. We see higher improvement for the analysis, lower atmosphere plus gold analysis state. So yeah, that was for, like, for only locations of other gold observations. And this one, what I'm showing is all the longitudes and with respect to day of year, all the 5 days of observations for a particular pressure level close to 194 kilometer. And in this one, the top one shows the lower atmospheric temperature minus true temperature, and the bottom one is gold temperature minus the true temperature. So having a different smaller means that is working better. And in this one, we see that the compared to lower atmosphere, when we assimilate gold, the values are smaller, and that means that the assimilation is doing much greater job. And in between these two lines, where most of the gold observations are available, we see all the lowest differences are occurring in this sector. And that is because gold observations are available in this sector. But in addition to that, we see that it also improves the other longitude outside these two lines where gold observations are not available. So this shows a promise that we can do some tidal analysis and see how some of the global tides are behaving. And so this is one example of the global tide DW1, so which is diurnal westward wave number 1, right? And that is for different lines are for different experiments. So the green one is the true, and red is our one assimilation include the gold observations, and blue is where we only have lower atmosphere assimilation. So compared to lower atmosphere only assimilation, this the red one is showing a bit closer to the true, though they are still away from the uh, true state. That's because of the other longitude we don't have data, and also f10.7 was higher for this one. And this on the right, what I'm showing is the local tide for a particular location and for all these three experiments. And on the local tides where we do have observations, we see that the red one is much closer to the true. So overall, like TD assimilation improving the local tides and global tides. By the local one is improved by 20% and global is 7%. And since we do have also like also check the densities in the simulation, and we have observed that like the red one, which is true minus lower atmosphere plus cold, so that value is smaller compared to true minus lower atmosphere. That means the neutral densities in the thermosphere are also improved, and there is like some higher difference in the lower altitudes. So that goes to like the whole observation starts to observe from around 130, 140 kilometers. So, but overall, on average, we see improvement, about 6% improvement in thermospheric neutral density. And so, and then we come to one of the comparison, how we do see the improvement in the ionosphere. And this is one particular hour of data for the whole globe, all longitude versus latitude for a particular ET is shown. And the top one is the true state, and the middle one is the lower atmosphere plus gold, and the bottom one is lower atmosphere only assimilation. And if you see that some of the structures like this one get generated in the lower atmosphere only assimilation is actually not present in the true state, but it was not produced in the lower atmosphere plus cold assimilation. So this shows that we do see some improvement in the ionospheric structures, and overall we see that the densities are higher compared to the true state, electron densities, and that's because these two rounds has higher F10.7 flux compared to this. And also, we did we did not update directly the ionospheric parameters, but it was like update was indirect through through the dynamics of the model. And so Yeah, we have seen like a lot of improvement in the uh, from the observing system simulation experiments, both in TC, density, tides, and in temperatures. The next step is to assimilate the actual gold temperatures and see how it does. And for actual assimilation, what we are doing is we are doing three different experiments. So all of them, two of them are assimilation experiments, and one is control experiment. And this for the control experiment, we are using ST-WACAM-X. So it is specified dynamics WACAM-X, and we use as the realistic solar and geomagnetic forcings, and uh, it nudges the WACAM-X state with the mirror to observations. And for the assimilation experiments, in one experiment we are using all the lower atmospheric observations plus cold T disk, and we are updating only the temperature. And in the second assimilation experiment, like the solar and geomagnetic force are same as the first experiment, and everything almost observations that are simulated are also same as that of the experiment one. But in addition to updating temperature, we are updating some of the neutral and ions like O, O2, and O positive. And this is the um, gold standard for this particular assimilation, because this will show a much better improvement compared to this one, as we'll see in the next slides. So now, in this one, what I'm showing is actually the validation of the assimilation. And I'm showing here three different plots. The top one is actually gold T disk for a particular longitude. This is 48 degrees west. And the x-axis is the local time for this particular location. And the top one is gold T disk. The middle one is uh, effective temperature from the experiment one, and the bottom one is the effective temperature from the control run, the ST-WACAM-X. And if we compare them, what we can see is that some of the fine structures that are better available in the assimilation run compared to the ST-WACAM-X. And overall, we see some of the broad latitude structures or long local time structures matches well between all of them. And this was for one particular day, and on the right side I'm showing is for another day. This is on 5th November. And this day was actually, there was a moderate geomagnetic event. And on that day, we can see that the comparison is much better with the data assimilation. So there are much more difference with the ST-WACAM-X. And I will show further quantification of this in the next slides. So this is just comparing gold T disk with the assimilation temperature. So we have updated the temperature with temperature and comparing the temperature again. So this shows good that many of the structures are matching. And in the next one, so what we are doing is here we are comparing the gold O by N2 with the assimilation or control simulation O by N2s. So in gold O by N2, which is not assimilated in the current assimilation. In the current assimilation, we have only simulated the temperature. And so comparing them with the gold O by N2 is like completely a different kind of data that been compared, because retrieval algorithm of O by N2 is completely different from the T-disk. And so it's a completely independent data set. And this is the O by N2 from the one of the data assimilation experiment. And we do see like some of the structures like northern high latitude, the enhancement in O by N2, which is actually a seasonal feature that is reproduced in the assimilation experiment. And this is also available in the control simulation, ST-WACAM-X, the bottom one. And some of the latitude features are better reproduced in the assimilation experiment 1, which has updated only temperature. And this is our ultimate assimilation, that is the experiment 2, which had updated temperature plus other states like the OR2 and O positive. And in this one, we do have better similarities with the gold observations. And this was for a quiet day, and on the right, we am showing it for a geomagnetic disturbed day. An interesting thing that you can see on a geomagnetic disturbed day, both the higher in the northern latitudes, you see strong depletion in the gold over N2. And that is nearly absent in the ST Wakame, but somewhat present in the D experiment 1, and is better present in the experiment 2. And that shows that assimilation improves the O by N2, which is not being assimilated in this particular assimilations. So yeah, feel free to stop me any point, if you have questions, or note down the slide number so that I can reach to the slide immediately. And so this was with the O by N2, and now I'll go to some of the quantifications. So what I'm showing here is scatter plot of T-disk with respect to data assimilation effect temperature. And the red points are actually very high density points. So we see that most of the high density point falls in the correlation 1 line. And that shows that the T-disk is driving the simulation in the right direction. And on the right side, I'm showing the comparison of gold O by N2 with the data assimilation experiment 2 O by N2. And we do see there is some improvement that we can quantify when we compare with the control state. But overall, we see that the gold O by N2s are a bit higher. And so in the bottom one, what I'm showing is same as the top one, but with respect to the ST Max. So gold temperature compared with the ST Max, and here the gold over N2 compared with the ST Max over N2. And overall, you can see for the ST Max, high density points are somewhat like this kind of line. And for the over N2, you see they are they're spread a lot in the axis where ST Max is. So they are higher value. There is a bias seems like here. But overall, compared to this state, we see that the assimilation improves by N2. And this is the statistics for all the 9 days of observations between 10 and 20 UT, where most of the disk observations are available. And so, and then we did another quantification of the, other than the scatter plot, we can do quantify based on the RMS error. And what is shown here is the RMS error from all the 3 experiments that are compared with the cold and disk temperature. So the blue one is the ST Max compared to the T-disk, and the red is the experiment 1, and the green is the experiment 2. So since both experiment 1 and 2 updated the temperature, so the temperature case, they are nearly the same. And compared to the ST Max, we did a lot of improvement in the RMS error. And these are for different days. So, and there was a geomagnetic storm on the 5th of November. And during the geomagnetic storm, we do see improvement is much higher, but overall RMS errors are also higher. And on the right is the same quantities, the same kind of RMS error, but for the O by N2. And we do see overall that the OIN2 from the assimilation experiment 2 is better compared to the ST Wacom X. So these are the numbers. So about overall we see about 13% improvement in effective temperature and OIN2. And so then, yeah, so both OBI2 and TDs, they are from the gold mission. So then we went on to see a very independent data set, which is not from gold mission. So for that, we use like GNSS TSA. So the bottom one, what I'm showing is on the x-axis is the days and y-axis is latitude. And this is for a particular longitude sector. So this longitude I have chosen because the GNSS TC is much better available over all this latitude in this longitude sector. And so the bottom one is GNSS TC, and this one here that you see is the data assimilation experiment to electron column density. And electron column density is equivalent to TC, but it's just um, for the ionosphere up to the top of the Wakamax, which is about 500 kilometer. And overall, we do see some of the fine structures matches between the data assimilation and the TEC. And if we compare same thing with the, this one is for experiment one, and this is for the ST Wacom X, the top one. And if we compare them, like overall, we have seen a better agreement with the data assimilation experiment too. And so further quantification of this done with like showing this same electron density and TEC for different, for a particular location. Like in this case, I have chosen a 0 to 10 degrees south latitude, and longitude is the same because in this longitude we have better data. And so here all these lines are for the different assimilation ST Wacom-X. The but the interesting or the most notable things are the red one and the blue one. So blue one is the GNSS TC, and the red one is the experiment to data assimilation TC. And you can see most of the places they overlap with each other. And also some of the like local structure like two minimum in the TEC in the blue one can also, sorry, two maxima in the TEC can also be seen reproduced in the both the data assimilation experiment. And in some places they nearly overlap each other. And so this is for particular location. And the bottom one is showing bias, sorry, RMS error between the data assimilation and GNSS TEC. So here also the best one is the red one, which is experiment 2. And overall we see that the experiment 2 has lower RMS error, the red one, compared to the blue one. And most of the higher values in the red occur during the night sector, like this here, this here, and those are because night sector with gold does not have a data, or gold does not have a T-disk observation. And so then we did a further quantification of how the RMS error and the bias changes with respect to latitude. And here, again, all these 9 days of data are shown on 1 to 9th November 2018. And the longitude is restricted to the 55 or 65 west. And these RMS error, again, are calculated with respect to GNSS TC. And the blue one is ST experiment. And the red one is again experiment 2. And overall, we can see at all the latitudes, the lowest RMS error occurred in the red one, which is showing the experiment 2. And that means the experiment 2, which is updating the temperature plus some of the neutral densities, improves the ionosphere better. And one more thing that we can see is that the high latitude, some of the high latitude, like, no, so in the bias cases, for the bias, the lower one, we do see again the same color is the same for all the observations. And here we again see that the red one, which is that assimilation experiment 2, has better bias, but at some places, particularly in the southern hemisphere, it is not as good compared to the experiment 1. And overall, the bias is higher in the higher latitudes, like mid latitudes, mid and high latitudes. And that was because in one of the previous slides, we have seen that the O by N2 has higher difference compared with the assimilations. And that, since O by N2 is proportional to TEC, so we do have higher bias in the TEC also in the high latitudes. And the percentage wise, we have seen improvement in RMS error is about like 8% compared to ST experiment. So, and for the bias, the improvement is about 60% for the ST experiment too. So that shows like an independent, we can validate the assimilation with an independent, completely independent data set. And we do see much better agreement with the independent data set. And since we do have some of the global data sets, so we can quantify the some of the global tides. And what I'm showing here is this 9 days of data, waves from all these 9 days of data. And these different components are like DW1, diurnal tide, westward propagating wave number 1, and similarly SW2 and other components. So overall, we see they have like a as per expectation amplitudes. And when we compare them with the ST Wacom X, we do see like on an average there is smaller values uh, in the in these tides, and for particularly for some of the components higher value, particularly this one SE2, that one is right, no, sorry, red one, and DE1. DE1 has a higher value in the Wacom X dart assimilation. And there are some differences, and this was for a particular location in the altitude with respect to altitude. And we did check how the SW2 varies with respect to latitude. And overall in the latitude features, like the top one here is ST Wacom X, and here bottom one is the Wacom X plus dart SW2. And note that the color bar is 2 kelvins smaller in the bottom one compared to the top one. So overall, the amplitudes are 2 Kelvin, 2 to 3 Kelvin lower in the bottom one. And some of the latitude and altitude structures, the broad ones does match, but there are some fine scale differences, like these structures seems like matching with a lower one, like this one. And some weaker values at different altitudes that can also be seen. So, frankly, we do not know which one is more realistic, which amplitudes are more realistic. But from the previous results that I showed in the previous slides, that some of the thermosphere OBN2 and TEC are better in the Wacom chart. So I would say like probably this one is the better one. The Wacom chart amplitudes or the latitude altitude structures are more realistic. Okay, so now I come to the summarize my talk. So we do see we have assimilated observations from stratosphere to the thermosphere in a whole atmosphere model. And particularly for the thermosphere, we assimilated the disk temperature, and we have seen that it improves the model state and the dynamics and the ionosphere. And particularly, we have seen that from the OC experiments, the tides are improved by, like the global tide is improved by 7% and local is improved by 17%. And actual assimilation of TD shows improvement in both thermosphere, ionosphere parameters. And this shows like the the assimilation using gold TDs improves atmosphere, ionosphere, and that can be used to study the ionosphere or atmospheric coupling and space weather effects. So yeah, conclusion is I think it's again redundant, but like it all this TDs assimilation improves the thermosphere, ionosphere, and here some of the future directions. So in this work, we did not assimilate Y and 2, but in future we would like to include the Y and 2 in the assimilation and see how it does it improve some of the high latitude biases that we see in the TC comparison. And also we would like to study some of the ionosphere thermosphere coupling and forcing effects. And so this result shows a promise that we can improve the nowcast and forecast of the thermosphere atmosphere using gold measurements. And with that, I thank you all for your patience.
Thank you, Fazlul. Does anyone have any questions? Okay, so I think there are several. Dan, why don't you go first?
So you've identified biases in the SD-WACM. How would you go about improving SD-WACM to reduce those biases? Is there hints in your analysis about where the model is deficient?
Yeah, this is a nice question. I will forward it to Nick. So I don't have idea how can we improve some of the dynamics in the WACM X itself. So Nick, if you have a quick answer, please go ahead.
I don't have direct answer at the moment, but yes, I think ideally we can use information from the data assimilation adjustments in terms of where the model might be deficient. You can use that not only for gold temperature but other areas as well. But of course, then figuring out what exactly you need to fix gets complicated.
Thanks, Nick, for the answer.
And Astrid, why don't you go ahead? And then there are a couple of questions in the chat that I will read afterwards.
Yeah, thank you. Very nice talk, very comprehensive. I might have missed it. Did you also look at the neutral wind changes due to assimilating the temperature, like the mean wind, as well as the tidal winds?
Yeah, so that we didn't do it. Like, yeah, that can be done, and we didn't do it so far. So far, we have been concentrating on where we do have actual observations available to validate it. So yeah, we can do that using icon winds, but for that, like for this particular duration, we do not have icon wind because icon started fighting late 2020, I guess, or early 2020. So
okay, thank you.
Yeah, but this is doable in the future.
And so then there are some questions in the chat from Ben Johnson. He asked, in the Aussie experiments that you presented, what was the reasoning for having the ensemble mean F10.7 set nearly 2 sigma above the truth run? So the truth was 76 versus 100 solar flux for the Aussie runs with a standard deviation of 15.
Okay, so the main motivation was to use a different F10.7 so that the temperatures and the ionosphere get a bit higher than what we expect from the true state. And using the true state, how it can improve how it can drag those temperatures towards the true state. That's what we wanted to see. And that is why we kept those numbers like 25, about 25 SFU higher. And the spread in the ensembles that we kept 15 SFU was just to spread the different ensemble members. So that's why we use those 15 as standard deviation. And I hope I answered. If not, you can come again.
Yeah, if not, he can follow up. And his second question was, were there areas of the DART documentation that you used, and if you have any comments on anything that should be rewritten or improved upon?
DART document, okay, that's like, yeah, so initially I found like it's very tough, but when going through it, like slowly when I started to work, I found it very helpful. Thanks for that. Like, yeah, I need to think about it. Like, I have to go through the documentation again and to find out. So sorry, I don't have a good answer for that, but it was very helpful, that one. That's what I can say.
And then Federico Gasparini had a question. He said, thanks for the nice talk. And he's wondering if you have plans to assimilate the ICON data, and if so, what observations you would consider most critical to improve specification, the background, the ionosphere and thermosphere state, and forecasting skill. And maybe it's better if I actually answer that question.
Okay.
So Federico, Chiting Su, who's postdoc here at HAO, has been working on assimilating the ICON data in WACM-X and DART. Which is one paper recently accepted, and I think it's already on the website in JGR Space Physics, and then another one that's under review. So I would probably point you to that, and that's assimilating the ICON wind data, and we see good impact in terms of the constraining the winds, and then also the impact on the electrodynamics as well. Hopefully that answered your question. If not, follow up in the chat. And Hanli, you have a question?
Yes, I was curious if when you did this, assimilation of both lower atmosphere and gold, and only lower atmosphere, and compared to SD, did you do any experiment of only assimilating gold with with either SD or without assimilating the lower atmosphere? What's the impact there?
Yeah, so for this particular assimilation, we didn't do just the gold, and even with the OSC also, we didn't just do that, just gold. But in the OC, like as you can see in the present slide where I am, so in the one experiment, we included only the lower atmosphere, and the other one lower atmosphere plus gold. Yeah, and he was suggesting another one just using just gold TDs, but we didn't do that. But from these two ones, like we do see that the gold TD improves the assimilation, like particularly from this kind of plots. So yeah, that's it. Like there are different combinations we can try. A lot of combinations possible. We try some of them, not all of them.
Yeah, I was just curious about the potential different timescales of their impact, whether, for example, the gold or thermosphere measurement would have shorter range of impact or not, compared to the lower atmosphere impact.
Yeah, that can be checked. Thanks for the comment.
Thanks.
Does anyone else have any final questions? Sounds like no. So thank you, Fazlul, for a nice talk again.
Yeah, thank you very much. Thank you all for your attention.
Thank you.
Thanks. Bye.